Alright guys, let's take a look at section 3.2 linear functions. And by the end of this, we want to be able to identify, evaluate, graph, and write linear equations. First thing we're going to talk about is function notation, and that's really just a fancy way of writing the equation. We're going to write these in slope-intercept forms typically, and instead of just what we're used to, maybe the y equals mx plus b, function notation is going to write that as a function of the input. And so we'll say f of x, function of x equals mx plus b. So that's really the only change there with the function notation. And then we're going to talk about linear functions, which we're already familiar with. Any function whose graph is a line. So let's take a look at some examples. In the first couple examples, we're looking at evaluating functions in function notation. So what is the value of g of x? It's equal to 5x plus 1 when x equals 3. So I see my 3 right there equal to the value of x. I have x inside of that equation. So I'm going to go ahead and evaluate g of 3 because I'm substituting the x value with the 3. So 5 times 3 plus 1. So g of 3 is equal to 5 times 3, that's 15, plus 1. G of 3 is equal to 16. And let's take a look at the second one here. Okay, so what is the value of g of x equal to negative 2x minus 3 when x is 4? So we're just going to substitute in the 4 there for the x, and then we'll evaluate g of 4 is equal to negative 2 times that value. We're going to substitute in with the 4 minus 3. And negative 2 times 4 is negative 8. Subtract 3. So g of 4 is negative 11. Okay, so it's just substitution. Give number 3 a try, pause the video, and then check to see how you did. H of x is equal to 7x plus 15. Evaluate when x is 4. So h of 4 7 times 4 is 28. So h of 4 evaluates to 28 plus 15. It's going to be 38, and the 5 will be 43. Okay, next topic we want to talk about, we want to identify a function rule. In this particular problem, we're talking about bracelets that can be made, and we want to determine the cost to make some number of bracelets. So we see some data down here. This is arranged in a table. So we have our input and our output, our x's and y's, and we can see that as we make bracelets, we have this increase in cost. So the first thing we want to do if we're going to write a linear function rule is to make sure that this is constant. We want a constant rate of change. And really what we're identifying there when we talk about that is the slope. And we've got that formula, y2 minus y1 over x2 minus x1. That's our rate of change, our slope. And we can identify that from a table pretty easily just by looking at the change from one value to the next. So from 1 to a 2, the difference here is 1. From 3 to 2 or 2 to 3, the difference there is an increase of positive 1. From 3 to 4, difference is 1. And then we relate that to the difference here on the output, 17 to 32, that's a change of 15, 32 to 47, and 47 to 62. So we see we have this constant change then of y values, my output of 15 over 1. So I have a rate of change or a slope of 15. So in this particular problem, that's talking about the cost of those bracelets as we move forward. So for each one, it's costing me an additional $15. So let's find the actual function rule for it. That's just our equation in slope-intercept form. So I have it y equals mx plus b. 4 quantities inside there. That's a y, m, x, and b. So I've already found my m. I'm going to go ahead and label that. And I've got all these coordinates representing x's and y's. So I'm going to go ahead and use the first one just because it's smaller numbers. So we'll plug in that 17 and a 1. And then I begin to substitute into my equation here. And I see that the b value is 2. So then my equation for this is simply just y equals my m, 15 times x, plus 2. And if I want to change this into a function rule, all I do is I swap out this y. I'm going to go ahead and write it as f function of x. So the only change there in this is that the function rule is simply replacing that y, that output, with f of x, that notation. Let's try another one here in example 5. So we'll do the same thing. We're looking at the change here between one and the next. So I have a change constant here of 1 from 6.5 to 13. That looks like a change of 6.5. Looks like a change of 6.5. And 6.5. So that slope then, that rate of change, my change in the y component over the change in the x, is just 6.5. So we'll go ahead and get our formula here, mx plus b, identify what we know, what we need to know. So I've got an m value of 6.5. I'm going to take a point on here. I guess we'll stick with the 1 for the lower, so 1, 6.5, and we need to find b. So let's go ahead and substitute in. So in this case, we see when we subtract 6.5 from both sides, b is 0. So then my equation, y equals 6.5x. I could write plus 0, but we typically don't, so we're going to go ahead and leave that off. And then to change it into a function rule or function notation, we just put f of x equals 6.5x. So again, the extension here, the change there is we are changing our y equals from slope-intercept form to this function notation. Okay, let's give number 6 a try. And we get the function using function notation as f of x equals 3x minus 2. Okay, taking a look at the story problem here as we analyze the linear function rule. So Tamika records the outside temperature at 6 a.m. The temperature increases by 2 degrees every hour for the next 6 hours. If the temperature continues to increase at the same rate, what will the temperature be at 2 p.m.? So first off, we have a change of 2 degrees every hour. That is a constant rate of change. So that just identified our slope. So we're going to write that function rule, or a function using function notation. So we've got our equation. just identified slope from the problem. It's a change of 2 degrees every hour. And it looks like here they give me some additional information. We started, or we are at -3 degrees. That's an initial value. That would be my y-intercept. Okay. So we now have everything we need to write our equation. The only two things I need for slope-intercept form were the slope and the intercept. So I didn't have to use additional points. I didn't have to find anything else. So we're just going to go ahead and substitute this in. So y equals my slope times x minus 3. And then we're going to rewrite it as, this one we could call t of x if we wanted to. Since we're talking about temperature, it doesn't always have to be f of x. T of x is equal to 2x minus 3. So again, don't make it harder than it has to be. All I need for an equation here in slope-intercept form is going to be that slope, and then the y-intercept, which is an initial value. So at 0 time, or whatever it is you're looking at, that initial value, is going to be your y-intercept. So in this case, the 2x minus 3. So now we're asked to sketch a graph of the function. So we're going to take that 2x minus 3. And when we plot these, we plot that y-intercept first. And then we're going to use our slope to find additional points. Remember, slope is just rise over run. So we come here on the y-intercept. Your x is on the horizontal, y is on the vertical. I have -3. Plot my first point. Then I have a slope of 2. So a slope of 2 as a rise over run, that is 2 over 1. So from this point, I rise 1, 2, and I run 1. There's another point on my line. 2 points I've got in my line. I'm going to go ahead and make a couple more here. 1, 2 over 1. 1, 2 over 1. And we've got our line. Next part right down below here, we're asked to evaluate when the value of x is 8. So let's go ahead and substitute that in. So I've got f of x is equal to 2x minus 3. And I'm evaluating at f of 8. So again, if you were thinking about this graphically, you would just go over to 1, 2, 3, 4, 5, 6, 7, 8, go up to your line, and that would be your output. That would be the value. We're going to go ahead and find this algebraically. So I substitute in an f of 8 is equal to 2 times 8, that's 16 less 3. So it looks like f of 8 is 13 degrees. Now, think about this given some context. Does using a linear equation or a linear function realistically represent the temperature for a domain of 0 to 24? So this is a realistic domain because x, we're talking about time, in this case hours of a day. And this is based on the context of the above problem from 6. So that makes sense. I can have 0 hours, so my initial time up to 24. That's going to roll into the next day. But to model this using a linear function where it's continuing to increase at a constant rate of change probably doesn't make a lot of sense in the terms of temperature over the course of a day, because it warms up typically as the sun comes up during the warmest part of the day, and then as it sets and into the evening time, it cools back down. So the answer to this is it's probably not realistic given sunrise and sunset. Temperatures typically decrease. Let's get rid of that. Temperatures will decrease as the sun goes down. Okay, let's look at two more examples graphing, give them a try, and then check your answers. Again, these are in mx plus b. Plot your intercept first. So I have a +1, and I use my slope as rise over run. This is a -1 right there. So as a slope, that's -1 over 1. Negative tells me I go down, so I go down 1 over 1. Down 1 over 1. Make a couple points there, and we'll draw our line. And b over here, 3x plus 1. So again, we're going to go up to +1. That's my y-intercept. I set my point, and I have a slope of 3. That's a rise of 3 for a run of 1. Rise of 3 for a run of 1. And all I need is 2. I just made an extra one. Not a problem. You can just make 2 lines, or 2 points. You've got your line. Okay, so let's look at the final problem here. Chairlift starts, looks like half a mile above the base of a mountain, and it travels up the mountain at a constant speed. So that's what helps me identify a constant rate of change, that it is linear. How far from the base of the mountain is the chairlift after 10 minutes? So let's evaluate, think about what we know and what we need to know. Okay, so looking at everything we're given here, I know that it starts at 0.5 miles above the base. That's going to be my initial position. So again, when I'm thinking about this, I'm thinking about an equation. These are linear, mx plus b. We're going to write it as a function. We'll change it into function notation. And I'm going for 10 minutes. It has a constant speed. That's telling me it's linear. It's a constant rate of change. And then from the graphic here, I see I'm half a mile from the base camp, and the chair travels 6 miles per hour and takes 15 minutes to reach the top. So I've got this travel time, or this domain, in the context of this problem of 0, right? I've not started traveling up the chairlift yet, and then all the way up to 15 minutes. So that's kind of the reasonableness of my domain within this particular scenario. And if we go ahead and think about this, so I need to find my rate of change. My initial position here, that's going to be the b value. That's my intercept at the starting time. I'm half a mile away, so I already know b, but I need to find m. And m is kind of given to us right here. It's traveling 6 miles per hour, but then we're talking about minutes. So I've got to do a conversion here. So I know it's 6 miles per hour. So a little dimensional analysis. So 6 miles for every hour, and I know that 1 hour for every 60 minutes. Okay, so if I multiply these through, I get 6 times 1 and 1 times 60, so that ends up being 6 over 60, which equals 1/10, 0.1. So there's my slope. So all I did was make a conversion. I converted it from miles per hour to essentially miles per minute. Okay, your hours would cancel out, and you have miles per minute. So that's the rate at which I'm traveling, 1/10 of 1 mile per minute. So then we just go ahead and plug it into our formula here. I'm going to go ahead and change my y equals to function notation. Right now we're talking about distance, so I'm going to use d. So d of x. You could use f of x, it really doesn't matter. Just understand that that variable up front can change. Since we're doing distance, I'm just going to use the d. So d of x is equal to my slope times x plus the half a mile. So that's my function that models this situation. And then it wants to know how far I will be after 10 minutes. So now we just evaluate it. So I have d of 10 is equal to 0.1 times 10 plus 0.5. And 1/10 times 10 is just 1. So d of 10 equals 1.5. And we're talking miles is our unit. So at this rate of 6 miles per hour, starting a mile, or excuse me, a half a mile from the base camp, after 10 minutes, we'll have traveled 1.5 miles. Okay, give example 11 a try, pause the video, and then check your answer. It wants to know how would the function graph and equation change if the speed is 4 miles per hour. So the only difference here is that the speed has changed from 6 down to 4. So we'll do the same thing. So I had my, let's see, 4 miles per hour. So again, we're going to have to do a conversion here per 1 hour times 60 minutes. Sorry, I flipped that. Need your hours on top to make sure that it cancels with the bottom. 1 hour is 60 minutes. See how your hours would then be eliminated. I have 4 times 1 over 60. So I have 4 over 60, that's 4 miles over 60 minutes. So I have 4 divided by 60. And that is 1/15. Okay, miles a minute. Okay, so a little bit slower rate instead of being 1/10. I'm going to use 1/15 instead of that decimal since it's a repeating decimal. 1/15 will give me a slightly more accurate answer. So there's my M. Your B is still, so we have now D of T is equal to 1/15 x plus the half mile. So does this have any bearing on the effect of the domain? So we're talking about those x values. Okay, so I mean it's going to adjust what is our x. If we were talking about this graphically, we're talking about, let's see, x and the y-axis. Over the x-axis, you would have time, and the y-axis you would have distance. Okay, and you would start, say, half a mile away. So however this is marked up. So over your domain, so the change here is that we're now going to take longer because we're going slower. So the realistic domain of this will be extended, right? It's going to take us a little bit longer to get there. And the distance, it's not going to change anything in our outputs there, but it will affect the domain. So let's go ahead and see when we evaluate this, d of t, and t is still 10 from the same example, but now we're going at a rate of 1/15 a mile a minute instead of a tenth. So when I take that 1/15, I get 10 over 15, so I get 2/3. And 2/3 is 0.66, and I'll get 0.66 plus the 0.5. We get approximately 1.16. Okay, so after 10 minutes in this example, when I've changed my speed to 4 miles an hour, I'm only traveling 1.16 miles. Previously, in the last example, when I was going 6 miles an hour, I traveled 1.5 in that same length of time. So your domain is going to be extended here in terms of reasonableness, but really it doesn't change a great deal because we're still talking about the same thing. Your speed has just changed. But the other real difference here in this compared to the other is your slope. So since previously I was going 6 miles an hour, that might have looked something like this. And when I decrease it to 4 miles an hour, that's now not as steep. So it's less of a slope, so your line might tilt down a little bit more. So it wouldn't be as steep as the last one. So that's going to change in the graph. Okay, so that's it for 3.2 linear functions and function notation. If you have any questions, bring them to class and we will get some practice on MXL.